All right, chemistry class, so this is your solutions video for day 45 and 46, assigned on Tuesday, April the 28th, and this is also for Wednesday, the 29th, and so it's a two-day assignment. Altogether, this assignment will take you about 30 to 40 minutes, so it'll keep it well under the 30 minutes per assignment. It's due on Monday, next Monday. If it's turned in after Monday, then you can get up to 80% credit, but for full credit it needs to be turned in by next Monday, and it's not accepted at all after May the 18th. And I'm going to be strict on those because I don't want to get 1,000 assignments in the last week of school, so you need to stick to those not accepted after dates, and really to the due dates in general. Okay, so there was a video that went with this that's in this same assignment. So watch that video. It'll answer most of these questions, but not all of them. So let me go over them. Avogadro's number and a mole are both the same thing. It's 6.022 times 10 to the 23rd. It's simply a number, but generally in chemistry, it's a number of atoms or a number of molecules. Why do we use it? Because it's big enough. It's a big enough number that we have a big enough collection of atoms or molecules that we can actually see the substance, weigh it, hold it in our hands. It's something we can actually work with. We can't work with single atoms and molecules. They're too small. So that's the reason why we use that big number. Now, the problem with that big number is it's too big to count. We can't count a number of atoms or molecules, so we need to get to it. We need to figure things out in an indirect way, and that's by knowing the atomic or molar mass. Okay, so what is atomic mass and mass number? Let me start with mass number. Let's say that I have a hydrogen, so there's a proton, and there's an electron, and that one electron and one proton represents a hydrogen atom. And occasionally, let me finish this. So the mass number of that, the mass number of this hydrogen is 1, 1. The 1 means it has one proton, and the one up on the top means it has a total mass of 1, because one proton has a mass of 1 atomic mass unit. So that would be called a 1, 1. That's the isotope notation for hydrogen, and it looks like that. Now, let's say I have a different hydrogen isotope, and occasionally, it's very rare, but occasionally you find hydrogen atoms that have a proton and a neutron. And there's the electron going around. So this is an H. The one on the bottom represents the proton. It's the atomic number. The one on the bottom is the atomic number, and the one on the top represents the mass number. It tells you what the mass of this hydrogen atom is. So it has a 2 because it has a proton and a neutron. You don't ever count the electron in the mass. It's too small. It doesn't really weigh anything. So let's say typically with hydrogen you have about 99 of these. Anyway, the mass number, let me finish the thought. The mass number are these numbers up here. It tells you what the mass of that specific isotope of hydrogen is. This isotope, again, isotopes are the same element, but they have different numbers of neutrons. This has 1 neutron, this doesn't have any neutrons. So that's the mass number, and this is the mass number for this particular atom. Now let's say you have 99 of these, and let's see, so 99 of these, what you call the standard hydrogen atom, and you have one of these, of the kind of rare hydrogen atom that has actually a neutron with it. If you took the average mass of 99 that have an atomic mass of 1 and one more that has an atomic mass of 2, you'd get a mass of approximately 1.01. And that's in atomic mass units. And you'll notice that that's the number of the atomic mass of a hydrogen atom when you look at your periodic table. It's 1.01. It's kind of a decimal number. Where does that decimal come from? Well, it comes from this, that most hydrogens are 1, but occasionally you'll find one that's 2. And if you average that 2 in with all the rest that are mostly 1s, you get a number a little bit bigger than 1. It just goes up a little bit. So that's called the atomic mass. Okay? So the atomic mass Okay, so the atomic mass is the average mass of all hydrogen atoms, whereas the mass number is the mass of a specific isotope of hydrogen. In this case it's 2, and in this case it's 1. So that's the difference between mass number and atomic mass. Okay, molar mass is okay, so molar mass is the same number as the atomic mass, but it's measured in grams. So example, the mass of a hydrogen atom is 1.01 AMU, the number we have up here. The mass of 1 mole of hydrogen atoms is 1.01 grams. So the reason that this number, 6.022 times 10 to the 23rd, is such a magic number is that it will give you the same exact numeric value, 1.01, 1.01. The only difference is the unit of measure. It converts from AMU to grams. No other number would do that. If you had a different number, you'd go from 1.01 AMU to some other number. So this one keeps the numeric value the same, and grams is what we work in the real world, and so it's nice to have that simple numeric conversion between AMU and grams. Okay, so that's the significance of molar mass. And finally, what is stoichiometry? I'll just write that down here. Okay, so stoichiometry is kind of a funny word, but it's the math of using chemical compounds, elements, and chemical equations. And you're going to see that later this week and next week, the use of stoichiometry. We're going to start working with chemical equations, and just like recipes in cooking, they will help us to tell how much of a certain element or compound we need to make how much of a different element or compound, just like a recipe. And that's called stoichiometry. So it's the math surrounding the use of chemical equations. All right, so now I'm going to move on, and we're going to put together some compounds here and figure out atomic and molar masses. If you want to print these sheets out, you can, or you can write this on lined paper. What I would like you to do is answer with complete sentence answers and learn to write the chemical compounds using both unit of measure and the compound name the way that you'll see me do here. Okay, so we're starting with carbon dioxide, and I've already filled out this table for you. So let's look at what this table's telling us. It's the element or compound is, to make carbon dioxide, you need carbon, oxygen, and that creates carbon dioxide. Now if you look at the compound formula, it's CO2. That means you need one atom of carbon, you need 2 atoms of oxygen, and that produces 1 molecule of CO2, not 3. You don't add these 2 together. That's the old analogy that I use. It takes 2 wheels and 1 seat to make 1 bicycle, not to make 3 bicycles. So these 2 put together to make 1 unit of carbon dioxide. Okay, over here we count and we multiply by the atomic mass. So it's 1 times, and for carbon it's 12. It's really 12.01. When I made this sheet, I rounded it off, but it really, on your periodic table, and I'd like you to use the decimals, it should be 12.01. Oxygen, 2 oxygens actually are exactly 16, and so 2 of them are exactly 32. And then if you add them together, you get 44. Again, technically it's 44.01. All right? Now, what this is saying is, from here, this area, to this area, you're multiplying by this number, 6.023 times 10 to the 23rd. So instead of 1 atom of carbon, you have 1 mole of carbon atom, 6.022 times 10 to the 23rd. Over here, instead of having 2 atoms of oxygen, you have 2 moles of oxygen atoms, 2 times 6.022 times 10 to the 23rd. And finally, at the end, instead of having 1 carbon dioxide molecule, you'll have 1 mole of carbon dioxide molecules. Okay? And then the real magic of this number is right here. That the molar mass, the mass of that 1 mole of carbon atoms, is 12. In other words, it's exactly the same number value as the mass of a single carbon atom. The difference is a single carbon atom is measured in AMU. That is to say there's 12 protons and neutrons in a carbon atom, and so it has a mass of 12 AMU. And if you take a mole, this number, you end up with the same number 12, except it's in grams. And that's what all of our scales in chemistry laboratories are calibrated in. They work in grams. So it converts the exact same numeric value. This is the only number that will do that. 32 AMU for the 2 oxygen atoms, 32 grams for 2 moles of oxygen atoms. And finally, 44 AMU for the 1 carbon dioxide molecule, 44 grams for 1 mole of carbon dioxide. So if I weigh carbon dioxide in the lab on the scale and I have 44 grams on the scale of carbon dioxide, it means I know I have exactly 1 mole of carbon dioxide molecules. It also means I know I have exactly 1 mole of carbon atoms in those carbon dioxide, and I have 2 moles of oxygen atoms in those carbon dioxide, just by knowing the mass that I can weigh on a scale. And that's how we work in chemistry, or able to work with these particles, is by knowing their masses. And over here it's asking for the number of atoms or molecules. Well, if it's 1 mole, then it's 6.0 times 10 to the 23rd atoms of hydrogen. Over here it's 2 times 6 times 10 to the 23rd, or 1.2 times 10 to the 24th atoms of oxygen. And for molecules, it's 6 times 10 to the 23rd molecules of carbon dioxide is how many of those I would have. Remember, chemistry works in terms of numbers of hydrogens and numbers of oxygens matching up to make numbers of molecules. But we have to work in grams because it's the only way we can't deal with numbers this big. We can't deal with things as small as atoms and molecules, and we can't deal with numbers as big as moles. So we need something that kind of helps connect us, and that's by knowing molar masses. Will tell us how many we have. All right? Okay, so let's go ahead and answer these questions. So the only part of this sheet now that you're going to need to answer these questions are these last 2 columns over here, what I'm kind of putting in a box right here. We're only interested in the moles now. This was just kind of to get us over to here. And actually I should have put these last 3 columns. That's my mistake. So everything that these last 3 columns are talking about is centered around 1 mole of carbon dioxide. What does it take to make 1 mole of carbon dioxide? Okay, and by the way, I'm not going to ask you any questions about numbers of particles. That might be something we'll talk about. We talk about it, in an AP course, but we're not going to deal with that here. It's not any much really that much harder. It's just something we don't need to deal with right now. So let's correct some mistakes as we go along here too. This should have said how many CO2 molecules in 1 mole of CO2, and I'm going to make that correction. I'll put it up so by the time you see this assignment you might actually see that correction made. How many CO2 molecules in 1 mole of CO2? So in 1 mole of CO2 there's 6.022 times 10 to the 23rd molecules of CO2. So there are, and I'm going to use the full decimal numbers that I would like you to use. Okay, there are 6.022 times 10 to the 23rd molecules of CO2 in 1 mole of CO2. So a couple things to point out. There's no abbreviation for molecule. You just have to write the word molecule. Fortunately, you won't have to do it very much. You always write the unit of measure. That's what we're talking about. What is that number referring to? It's referring to molecules. And what's the substance? Because I'm dealing with carbon and oxygen and carbon dioxide. So which one am I talking about? So you're talking about unit of measure and what's the substance in 1 mole. Now it's funny how they do this, but the word mole is spelled M-O-L-E, but when you write it in a chemical equation, they chop off the E at the end, so it's M-O-L and CO2. So again, I have a unit of measure, mole, and the substance, CO2. Alright, so there are 6.022 times 10 to the 23rd molecules CO2 in 1 mole CO2. Okay, let's move on. How many grams is 1 mole of CO2? So there's 1 mole, and we see that 1 mole is 44 grams. So I'm actually going to write that differently. Okay, so there's 44.01. Again, I'm adding the decimal on that I didn't do up here. I don't care whether you do it in this table. Do it on the rest of them though. There are 44.01 grams of CO2, so unit of measure and the substance we're talking about, in 1 mole, unit of measure, CO2. Okay, how many moles of oxygen in 1 mole of CO2? So, here's 1 mole of CO2, and to make 1 mole of CO2, you need 2 moles of oxygen. So you need 2 atoms of oxygen for every 1 molecule of CO2. You need 2 moles of oxygen for every 1 mole of CO2. So there are 2 moles oxygen in 1 mole CO2. How many grams of oxygen in 1 mole of CO2? Well, again, everything here is referenced to 1 mole of CO2. Everything you see over here. So grams of oxygen. So you come over here to the oxygen row, and you come over where the molar mass is in grams, is right there. So it's 32 grams. Okay, there are 32 grams of oxygen in 1 mole of CO2. How many carbon atoms in 1 mole of CO2? See? Again, see if you can figure this one out. It's asking for carbon atoms. So you have to come up to the carbon row and go over to where it's giving us numbers of atoms way over here, because all of this is referenced to 1 mole of CO2. So there's that number. There's 1 mole of carbon atoms, which is that number of atoms in 1 mole of CO2. Okay, so there are 6.022 times 10 to the 23rd atoms of carbon, that's a mole, in 1 mole of CO2. So just so we don't have to keep saying 6.022 times, you just say there's 1 mole of carbon in 1 mole of CO2. 1 and 1. Okay, finally, how many grams of carbon in 1 mole of CO2? Again, we go to carbon. This is reference, everything here reference to 1 mole of CO2. So there you go. That's how many grams of carbon there would be in 1 mole of CO2. Okay, so there are 12 grams of carbon in 1 mole of CO2. And that's how you do these. They're not that hard, okay? It's just a matter of setting up this table. I would like you, if you do this on line paper, I would like you to draw this table. I don't care if you draw the lines, just make the columns, put the headings in, and write down underneath. But the lines, that's up to you. Okay, let's move on to the next one. That's going to be H2O.